Welcome to this problem walkthrough. In this session, we'll explore problem number 205, titled Isomorphic Strings. We'll break down the problem statement, analyze various approaches, and guide you toward an efficient solution. Let's dive in. In this problem, we are tasked with determining whether two given strings, S and T, are isomorphic. Two strings are considered isomorphic if the characters in the first string, S, can be replaced to form the second string, T, while preserving the order of characters. However, there are some important rules to follow. Every character in S must map to exactly one character in T, and no two characters in S can map to the same character in T. On the other hand, a character in S can map to itself. The input for this problem consists of two strings, S and T, and the output is a Boolean value. We return true if the strings are isomorphic and false otherwise. To make this clearer, let's dive into some examples, starting with the case where S is egg and T is add. For the input strings S equals egg and T equals add, the output is true. This is because the characters in S can be mapped to the characters in T as follows: the character E maps to A, and the character G maps to D. Since G appears twice in S, it consistently maps to D and T. This consistent one-to-one mapping ensures the strings are isomorphic. Now consider the next example, where S equals foo and T equals bar. In the case where S is foo and T is bar, the output is false. This is because the character O in S would need to map to two different characters in T, both at and are. This violates the rule that a single character in S can only map to one unique character in T. On the other hand, when we look at the input S equals paper and T equals title, we find that the strings are indeed isomorphic. For the strings S equals paper and T equals title, the output is true. The mapping of characters is as follows: P maps to T, A maps to I, P, already mapped, maps to T again, E maps to L, and R maps to E. Since all mappings are consistent and no two characters in S map to the same character in T, the strings are isomorphic. Finally, let's touch on some constraints and edge cases. The lengths of S and T are guaranteed to be between 1 and 10 to the power of 4, and they will always have the same length. Both strings consist of any printable ASCII characters, including letters, numbers, spaces, and symbols. For edge cases, empty strings are trivially isomorphic, and single character strings are also always isomorphic. It's important to carefully handle cases with repeated characters to ensure consistency. With these rules in mind, we are now equipped to solve the problem efficiently. To solve the problem of determining whether two strings are isomorphic, we considered multiple approaches. The first is the brute force approach, which involves comparing all possible mappings between the characters of S and T. The idea here is to systematically test if S can be transformed into T by consistently replacing characters. However, implementing this requires nested loops to explore all mapping possibilities, which makes it highly inefficient. The time complexity can easily reach n squared, or worse, depending on the details, making it impractical for even moderately sized inputs. We rejected this approach due to its inefficiency. Another approach is the hash map approach, which is both more efficient and intuitive. Here, we use two hash maps, one to track how characters in S map to characters in T, and another to track the reverse mapping from T to S. As we iterate through the strings, the key is to ensure that the mappings remain consistent in both directions. If we detect any inconsistency, we know the strings are not isomorphic. This approach has a time complexity of n, and uses n space for the hash maps. While it requires additional space, it is efficient for typical input sizes and avoids the inefficiency of brute force. An alternative to using hash maps is the single array approach, which optimizes space usage. Instead of two hash maps, we use two fixed-size arrays to track the last seen positions of characters in S and T. This works because the input consists only of ASCII characters, which allows us to use arrays of size 256. As we iterate through the strings, the algorithm checks whether the last seen positions for the current characters are consistent between the two strings. If there's a mismatch, the strings are not isomorphic. This approach also has a time complexity of n, but since the arrays are of fixed size, the space complexity improves to 1. However, this method is less intuitive compared to the hash map approach, as it relies on the fixed ASCII character set. For our chosen strategy, we selected the hash map approach. It's intuitive, easy to implement, and efficient for typical inputs. The key insight is that two strings are isomorphic if and only if each character in S maps to exactly one character in T and vice versa. The use of two hash maps enforces this condition effectively, making the solution both clear and reliable. While the single array approach is slightly more space efficient, the hash map method is easier to generalize, for example, to Unicode characters, which makes it a better choice overall. To implement the hash map approach, we start by initializing two hash maps, one for tracking mappings from S to T, and the other for the reverse mappings from T to S. Next, we iterate through the characters of S and T simultaneously. For each pair of characters, we first check if a mapping already exists in either hash map. If it does, we verify that the existing mapping is consistent. If no mapping exists, we create a new entry in both hash maps. By the end of the iteration, if no inconsistencies are found, we can confidently return true, indicating that the strings are isomorphic. Otherwise, we return false. This algorithm has a time complexity of O(n), where n is the length of the strings, as we process each character pair once. The space complexity is O(n), due to the storage requirements for the hash maps. While this approach uses slightly more space compared to the single array method, it is far more intuitive and generalizable. Ultimately, the hash map approach strikes an excellent balance between simplicity, efficiency, and scalability, making it the most practical choice for solving this problem in both interviews and real-world applications. The goal of this problem is to determine if two strings, S and T, are isomorphic. This means we want to check if each character in S can be consistently replaced to transform it into T. Importantly, no two characters in S should map to the same character in T, though multiple characters in S can map to the same character in T. To solve this, we start by understanding two critical requirements. First, every character in S must always map to the same character in T throughout the strings. Second, no two distinct characters in S can share the same mapping to a single character in T. To enforce these constraints, we will use two hash maps, one, S_to_T, to store the mapping from S to T, and another, T_to_S, to track the reverse mapping from T to S. These will allow us to efficiently check for both forward and reverse consistency as we process the strings. The next step is to iterate through the characters of both strings simultaneously. For each character pair, S, I, T, I, we need to verify the mappings in our hash maps. If S, I, is already in S_to_T, we check if it maps to T, I. If not, we know the mapping is inconsistent, so we return false. Similarly, if T, I, is in T_to_S, we confirm that it maps back to S, I. If it doesn't, this indicates a conflicting reverse mapping, so we return false. If neither character is mapped yet, we simply add the pair to both hash maps, S, I, T, I, in S_to_T and T, I, S, I, in T_to_S. Once we've processed all character pairs without detecting inconsistencies, we can confidently return true, as the strings are isomorphic. The key to solving this problem efficiently lies in our use of hash maps. These data structures allow us to perform lookups and insertions in constant average time, making them ideal for enforcing the bidirectional consistency of mappings. By iterating through the strings character by character, we ensure that every mapping respects both the order and consistency of the transformation. Additionally, by exiting early when we detect an inconsistency, we avoid unnecessary computation and improve performance. There are also several edge cases to keep in mind. If the strings have different lengths, they cannot be isomorphic, so we return false immediately. If both strings are empty, we return true, as there are no mappings to check. For single character strings, we also return true, since no conflicts can arise. We must also handle repeated characters in S, ensuring they always map to the same character in T. Finally, we need to detect conflicting reverse mappings, where multiple characters in S attempt to map to the same character in T. Let's take a closer look at the data structures and complexity analysis. We use two hash maps, S_to_T for the forward mapping from S to T and T_to_S for the reverse mapping from T to S. These hash maps ensure that we can efficiently verify mapping consistency with O(1) average lookup and insertion times. In terms of complexity, the algorithm has a time complexity of O, n, where n is the length of the strings. This is because we perform a single pass through the strings and execute constant time operations for each character. The space complexity is O, k, where k is the number of unique characters in S and T. This accounts for the storage used by the two hash maps. Together, these properties make the solution both time-efficient and space-efficient. To see the algorithm in action, let's walk through an example with the input s equals egg and t equals add. We start by initializing two empty hash maps, s_to_t and t_to_s. As we loop through the characters, the first pair is s, 0, equals e and t, 0, equals a. Since neither character is mapped yet, we add e dash a to s_to_t and a dash e to t_to_s. Next, for s, 1, equals g and t, 1, equals d, we add g dash d to s_to_t and d dash g to t_to_s. Finally, for s, 2, equals g and t, 2, equals d, we verify that g dash d is consistent in s_to_t and that d dash g is consistent in t_to_s. Since no inconsistencies are found, we conclude that the strings are isomorphic and return true. After processing all character pairs without finding any inconsistencies, the output for this example is true. This indicates that the strings egg and add are indeed isomorphic, as every character in S consistently maps to a corresponding character in T, and the reverse mappings are also valid. This example highlights how the algorithm ensures both forward and reverse consistency while efficiently handling the transformation process. This Python implementation solves the problem of checking whether two strings S and T are isomorphic. The solution uses two dictionaries to maintain mappings between characters of S and T in both directions. First, we initialize two empty dictionaries, map_s_to_t and map_t_to_s. These will store the mappings from characters in S to characters in T and vice versa. For example, if s equals egg and t equals add, the mapping would be e, a, g, d, for map_s_to_t and a, e, d, g, for map_t_to_s. The zip, st, function is used to iterate over pairs of corresponding characters from S and T. For each pair, char_s, char_t, the algorithm checks two conditions. 1. If char_s has already been mapped in map_s_to_t, we ensure that it maps to the same character char_t. If it doesn't, the strings are not isomorphic, and we return false. 2. Similarly, if char_t has already been mapped in map_t_to_s, we ensure that it maps back to char_s. If it doesn't, we return false. If neither condition is violated, we add the current pair, char_s, char_t, to both dictionaries to keep track of the mapping. Finally, if the loop completes without finding any inconsistencies, we return true to indicate that the strings are isomorphic. This approach ensures that the solution runs in O, n, time, where n is the length of the strings, as we only perform a single pass through the strings and dictionary operations are O, 1, on average. The use of two dictionaries ensures that the mapping is consistent in both directions, avoiding conflicts and guaranteeing correctness. This is the Java implementation of the isomorphic strings problem, number 205 on LeetCode. The logic mirrors the Python solution, using two hash maps to maintain mappings between characters of the two strings in both directions. Java-specific features like explicit type declarations and the map interface are utilized. The algorithm iterates through both strings simultaneously, ensuring the mappings are consistent, and returns true if the strings are isomorphic, otherwise false. To solve this problem, we start by examining the first example where s equals egg and t equals add. The first step is to initialize two empty dictionaries. The first, map_s_to_t, will help us track how characters in S map to characters in T. Similarly, map_t_to_s will track mappings in the reverse direction, from T to S. After the setup, we iterate over each character pair from the two strings. For the first pair, char_s equals e and char_t equals a, neither character exists in their respective mappings, so we establish the mappings map_s_to_t, e, equals a and map_t_to_s, equals e. Now, the state of the dictionaries reflects these mappings. For the second pair, char underscore s equals g and char underscore t equals d, we again find that neither character is mapped, so we add map underscore s underscore to underscore t, g, equals d and map underscore t underscore to underscore s, d, equals g. The state updates accordingly. Finally, for the third pair, char underscore s equals g and char underscore t equals d, we observe that both mappings are already consistent, as g maps to d and d maps back to g. This confirms that all character mappings so far align with the expected behavior. At this point, all character pairs in the first example are consistent with the established mappings. This allows us to conclude that the strings s and t are isomorphic, so we return true. Now, let's consider a second example where s equals foo and t equals bar. As before, we initialize two empty dictionaries, map underscore s underscore to underscore t and map underscore t underscore to underscore s, to track character mappings. Looking at the first pair, char underscore s equals f and char underscore t equals b, we find that neither character is yet mapped, so we add map underscore s underscore to underscore t, f, equals b and map underscore t underscore to underscore s, b, equals f. The state of the dictionaries now reflects this mapping. For the second pair, char underscore s equals o and char underscore t equals o, we again find no conflicts, so we add map underscore s underscore to underscore t, o, equals o and map underscore t underscore to underscore s, equals o. The mappings are still consistent at this point. Next, we encounter the third pair of characters, char underscore s equals o and char underscore t equals r. Here, we find a problem. O is already mapped to o and map underscore s underscore to underscore t, but the current char underscore t is r. This creates an inconsistent mapping, as a single character in s cannot map to two different characters in t. Because of this conflict, we determine that the strings s equals foo and t equals bar are not isomorphic. Therefore, the output for this example is false. Now let's move on to a third example where s equals paper and t equals title. Once again, we start by initializing empty dictionaries, map underscore s underscore to underscore t and map underscore t underscore to underscore s. For the first pair, char underscore s equals p and char underscore t equals t, we add the mappings map underscore s underscore to underscore t, p, equals t and map underscore t underscore to underscore s, t, equals p. The state of the dictionaries is updated to reflect this. For the second pair, char underscore s equals a and char underscore t equals I, we add the mappings map underscore s underscore to underscore t, equals I and map underscore t underscore to underscore s, I, equals a. The mappings remain consistent. Looking at the third pair, char underscore s equals p and char underscore t equals t, we see that p already maps to t and map underscore s underscore to underscore t and t maps back to p and map underscore t underscore to underscore s, so there is no conflict. For the fourth pair, char underscore s equals e and char underscore t equals l, we add map underscore s underscore to underscore t, e, equals l and map underscore t underscore to underscore s, l, equals e, keeping the mappings consistent. Finally, for the fifth pair, char underscore s equals r and char underscore t equals e, we add map underscore s underscore to underscore t, r, equals e and map underscore t underscore to underscore s, e, equals r. At this point, all character pairs align with the established mappings. Since there are no inconsistencies, we conclude that the strings s equals paper and t equals title are isomorphic, and we return true as the final output. To analyze the time complexity of the solution, we start by looking at the main loop. The for loop iterates through the characters of the strings s and t simultaneously using zip, s, t. Since both strings are of length n, this iteration takes o, n, time. Now, for each character pair, char underscore s, char underscore t, the algorithm performs operations on two dictionaries, map underscore s underscore to underscore t and map underscore t underscore to underscore s. These operations include checking if a key exists, looking up values, and inserting key value pairs. Thanks to Python's hash table implementation, these dictionary operations have an average case time complexity of 1. Since there are n character pairs and each involves a constant number of these operations, their total contribution is also n. Combining the time for the loop and the dictionary operations, the overall time complexity of the solution is n. Now, let's analyze the space complexity. The solution uses two dictionaries, map underscore s underscore to underscore t and map underscore t underscore to underscore s, to store mappings between characters in the strings. In the worst case, where all characters in S&T are unique, each dictionary will need to store n key value pairs, one for each character. This means each dictionary takes n space. Apart from these dictionaries, other variables used in the algorithm, such as char_s, char_t, and the loop counter, require only a constant amount of space, or O1. Putting this together, the total space complexity comes from the two dictionaries, each taking n, plus the O1, for other variables. Therefore, the overall space complexity is n. Let's consider how the time complexity changes in different scenarios. In the best case, the function detects an inconsistency in the character mappings early in the loop and returns false. If this happens after k iterations, the time complexity for this case is k, where k is the number of iterations before the inconsistency is found. On average, the function will go through all n characters, performing O1 operations per iteration, leading to n time complexity. In the worst case, the strings are traversed completely without any inconsistencies, as is the case when the strings are isomorphic. This results in a time complexity of n. To highlight the efficiency of the current solution, consider a brute force approach that tries all possible mappings between S and T. This would require generating and checking permutations, leading to a factorial time complexity of n, which is impractical for large inputs. By using hash maps, our solution achieves linear time complexity of n, making it far more efficient. Finally, let's solidify our understanding with a mathematical proof for the big O analysis. For the time complexity, let n represent the length of the strings S and T. The loop runs exactly n iterations, and during each iteration, a constant number of O1 operations, such as dictionary lookups and insertions, are performed. Multiplying the n iterations by the O1 operations gives us a total time complexity of n. For the space complexity, consider the two dictionaries, map_s_to_t and map_t_to_s. Each dictionary can store at most n entries in the worst case, where every character in S and T is unique. This results in n space for each dictionary. Since no other data structures scale with the input size, the total space complexity remains n. This efficient use of time and space makes the solution well suited for this problem. When working with isomorphic strings, there are several common pitfalls to avoid. One major mistake is failing to account for inconsistent mappings. For example, if a character in the first string maps to multiple characters in the second string, it violates the requirement of a one-to-one mapping. This inconsistency can lead to incorrect results. Another frequent issue is ignoring the reverse mapping. It's crucial to ensure that no two characters in the first string map to the same character in the second string, as this would create ambiguity and break the bijection requirement. Additionally, some implementations only consider the first mismatch and stop checking the rest of the strings. This approach can miss deeper inconsistencies that arise later in the strings. Finally, overlooking edge cases such as empty strings, strings with only one character, or strings with repeated characters can lead to unexpected runtime failures. These edge cases often expose flaws in the logic, so they should always be tested thoroughly. Inefficient solutions can also be a problem when solving this type of question. For example, brute force methods that iterate over all possible mappings can lead to a time complexity of n squared, or worse. This inefficiency becomes a problem when dealing with larger strings, as it may exceed time limits in competitive or interview settings. A key insight here is that this problem boils down to verifying a one-to-one correspondence between two sets of characters. The most efficient way to do this is to use two hash maps, one for mapping characters from the first string to the second and another for the reverse mapping. Instead of comparing every character pair manually, you can build these mappings in a single traversal of the strings, reducing the time complexity to n. It's also helpful to recognize that similar strategies, such as using hash maps or sets, are common in problems involving mappings, bijections, or transformations. During interviews, you should clearly explain how your solution handles both forward and reverse mappings, as this demonstrates attention to detail and a solid understanding of the requirements. Additionally, make sure your solution accounts for edge cases like empty strings, strings of different lengths, or repeated characters, as interviewers often test for these scenarios. This type of problem is closely related to several other questions on LeetCode. Examples include Problem 290, word pattern, which checks for a similar one-to-one mapping between words and patterns, and Problems 242 and 49, which deal with anagram verification and grouping, respectively. These problems share similar concepts, such as transformations between sequences or sets, and often rely on hash maps or sorting for efficient solutions. Turning to alternative approaches, the brute force method involves generating all possible mappings between the characters of the two strings to verify if the transformation is consistent. While simple to understand, this approach is computationally expensive, with a time complexity of n squared, or worse, making it impractical for larger inputs. A better approach is to use hash maps to maintain a consistent one-to-one mapping in both directions. This method is efficient, with a time complexity of n, and is relatively easy to implement. However, it does require additional space for the hash maps, which may not always be ideal depending on the constraints of the problem. Another alternative is the array-based approach, which is particularly effective if the characters are limited to ASCII. In this method, two arrays are used to represent the mappings, for example, one array for mapping characters from the first string to the second, and another for the reverse mapping. The indices of these arrays correspond to the ASCII values of the characters, making the approach both simple and efficient. The main advantage of this method is that it is more space efficient compared to hash maps, as it avoids the overhead of maintaining dictionary structures. However, this approach is less flexible, as it assumes a limited character set and cannot be extended to support non-ASCII characters without significant modifications. As with any solution, it's important to weigh the trade-offs and choose the method best suited to the problem's constraints and requirements. Great job making it to the end. To sum up, we explored how to determine whether two strings are isomorphic using efficient data structures like hash maps. Keep practicing problems like this to strengthen your skills with string manipulation and mappings. Don't forget to like, share, and subscribe for more content like this. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!